sklearn, linear model, orthogonal matching pursuit CV. Description. Orthogonal matching pursuit CV implements orthogonal matching pursuit OMP with cross-validation to determine the optimal number of non-zero coefficients and non-zero coefs for sparse signal recovery. It searches for the sparsest solution that fits the data by iteratively adding features with the highest correlation to the residual inputs. X feature matrix of shape n samples. N features. Y target vector of shape n samples. Outputs. Coa the estimated coefficients for the linear model. Intercept independent term in the linear model. N non-zero coefs optimal number of non-zero coefficients determined through cross-validation. Steps. 1. Split the data into training and validation sets. 2. For each fold in cross-validation. A. Train an orthogonal matching pursuit model with a specified number of non-zero coefficients. B. Calculate the performance metric e.g. mean squared error on the validation set. 3. Choose the number of non-zero coefficients that yields the best performance across the cross-validation folds. 4. Train the final orthogonal matching pursuit model with the selected n non-zero coefs on the entire training set. Metrics. Mean squared error MSE measures the average squared difference between predicted and actual values. R squared represents the proportion of variance in the target variable explained by the model. Visualization plots. Coefficient plot displays the estimated coefficients of the model, highlighting the selected non-zero coefficients. Fine-tune parameters. N non-zero coefs number of non-zero coefficients to be selected in the model. This can be a range of values for cross-validation, or a single value if it's already known. CV the number of folds for cross-validation. Uncertainty methods. Bootstrapping resampling the data with replacement and fitting the model multiple times to estimate the uncertainty in the coefficients. Challenges and fixes. Challenge 1. Overfitting when the model is too complex and captures noise in the data, leading to poor generalization. Sample use case that resulted in challenge 1 using a high number of non-zero coefficients or a small dataset. Fixes to challenge 1. Increase the size of the training data. Reduce the number of non-zero coefficients. Use regularization techniques like L1 or L2 penalties. Challenge 2. Feature selection bias when the feature selection process is biased towards certain features, leading to inaccurate model predictions. Sample use case that resulted in challenge 2 using a biased feature selection method or having correlated features in the data. Fixes to challenge 2. Use a more robust feature selection method. Remove correlated features from the data. Use feature scaling techniques to normalize feature values.